Now let's talk about distances, because that's the fundamental physical quantity that you need in order to convert observed quantities like fluxes into luminosities or angular size into physical size, and turns out to be the basis of all cosmological tests. Hubble himself already devised a bunch of these, and then more have been added at first. And you begin with these R of t curves as a function of cosmic time. Now, R of t is really 1 over 1 plus redshift, so that's just redshift in disguise. Now, measuring time, looking back at some galaxy at some redshift, is actually really difficult. So instead of measuring time, we use the distance, because this multiply the time with speed of light and you get the distance, right? Speed of light being constant. So then you can transform this diagram, and now the x-axis is the redshift, because that's a relatively easy one to measure. So the scale factor is now the independent variable, because that's what we can measure easily, and convert time into distance by multiplying it by speed of light. And so if you can measure how distances to different things change as a function of time, then you can map out this curve. And that's the job of cosmology. Now, this is curvature. The absolute scaling is given by the Hubble constant, but the shape of the curve is given by the other parameters, and by actually measuring what's going on, you can see which curve fits the best. So how do we get distances? All right. First, let me give you exact values for what Hubble length and Hubble time are. And here I introduce this scaling parameter, little h subscript 70, which says if Hubble constant is 70 kilometers per second per megaparsec, and it is within a couple kilometers per second, then Hubble length is 10 to the 28 centimeters. And Hubble time is 4.4 times 10 to the 17 seconds. Turns out to be about 13 or 14 billion years. And you can take formulae that are obtained from solving Riemann equation and follow how these things change in time. Now, in general, those have to be done as numerical integration. The integrals of these formulae do not have closed analytical solution, but this is a straightforward matter to do. And so here is how distance in units of the Hubble length changes out to given redshift. The three curves are three different cosmological models. The solid one is also called Einstein de Sitter model, where density is exactly equal to critical, and it's just matter and nothing else. And the dashed one is now with cosmological constant together with the matter adding up to omega of 1, and that's actually not so different from what it really is. And the last one is an almost empty universe, no dark energy, and just 5% of the critical density in regular matter. Because more matter means more gravity, more deceleration. Universes with higher density will be smaller at any given time than universes that are nearly empty. And cosmological constant can mess with this in either direction. So this is how we compute the distances, but that's not what we measure. What we measure uses either inverse square law for sources of light, those measure relative distances, or angular diameter as a function of distance in relativistic form. Now, you understand the inverse square law in plain Euclidean space, but now because the universe is expanding, things get a little more complicated. First of all, because the source is moving, there is a relativistic time dilation. time is stretched by factors of 1 plus redshift. And each photon gets stretched by that factor too. So if you compute flux from some source of luminosity L, it will be L divided by 4 pi times the distance squared, simple Euclidean case, and 2 extra powers of 1 plus redshift. One because of time dilation, one because of the stretching of the photons. So people bundle those and take real distance times 1 plus redshift and call it luminosity distance. And then that's the distance that you can use in relativistic equivalent of inverse square law. So if you had sources of light that are intrinsically same luminosity, so-called standard candles, then by measuring how the flux changes as a function of redshift, you can map that back how luminosity distance changes as a function of redshift. And that's called a Hubble diagram. Now here are our 3 cosmological models, and now plotting the luminosity distance, because it's real distance times 1 plus z, you can notice these numbers are higher. With regular distance, it was kind of 1 or 2 times the Hubble length. Now it's more like 10 times the Hubble length. And that's because of 1 plus z factor. Another thing that you can measure, and those are really the only 2 things you can measure, will be angular diameters. So if you have source of physical size x, and you put it at the distance of d, it will subtend angular diameter of x divided by d in radians. But if it's fixed in proper coordinates and universe has expanded since then it was bigger relative to the co-moving coordinates back then, in opposite sense of what happened with luminosity distance. So you divide the regular distance by 1 plus redshift, and we call that the angular diameter distance. So if you use that in relativistic equivalent over 1 over distance law, then you can compute how angular diameter will change. So if you had sources of standard size, and turns out the entire universe is a good one, and look how that length changes as a function of redshift, then you can map the relativistic version of angular diameter change and map that back again into the distance and then into the RT and so on. So these diagrams are what cosmologies are trying to map out by looking at relative distances to some kind of standardized kind of things. Supernovae turn out to be really good for this. We'll talk about that next time. Well, time after that. Now, we cannot measure directly how clocks are ticking in other places, but it's useful to know what's the age at any given redshift if you're doing things like galaxy evolution. So you measure cosmological parameters somewhere else, and that tells you how to map redshift into actual age. And here are our friendly models. The set of curves that is closer to the origin is the look-back time. So it's the age of the universe. And you can see that today, they're around 1 Hubble time, so that's about right. And the other is the look-back time. The further you look in the past, further you look in redshift, you also further look in the past. And the Big Bang happens at the redshift of infinity. So these curves have to bend over and flatten like that. You can also compute things how the volume changes. So if you are looking at some population, say galaxies in co-moving space, you can have how many are there per unit volume and then look at it as well. So that's what forms the basis for cosmological tests, to which we'll come back later. But this is the takeaway point, that cosmological models that have higher density and or negative cosmological constant are those that show maximum deceleration. Therefore, at any given time, universe is smaller in those models. Vice versa, for models with lower density and or positive cosmological constant, because accelerates expansion, they're always bigger at any given moment. So if the lengths are, say, smaller, that means the distances tend to be closer, regardless of whether luminosity or angular diameter distance. And so in the denser and or negative cosmological constant models, things would look bigger in the sky, and they'll be brighter in the sky. And because volume is smaller, there'll be fewer of them. And exactly the opposite if we're looking at low density models and or with positive cosmological constant. Those would be larger, things would look smaller, they would look fainter, and volumes will be bigger, so there'll be more things out at high redshifts. And so in this way, we can connect theoretical models with observational quantities, and that's how observational cosmology is done.